Welcome to lecture 7 of the course on deep learning CS7015. In this lecture, we are going to talk about autoencoders and we will focus on their relation with PCA, then talk about regularization in autoencoders, wherein we will look at denoising autoencoders, sparse autoencoders and contractive autoencoders. So, let us begin with an introduction to autoencoders, what they are. So, this is what a typical autoencoder looks like. And as you can see, this is very much like a feed forward neural network. You have an input which is xi. So, you are given some training data, you are given some I samples xi to xm. So, this is your training matrix x, which we have seen in the previous lectures. So, this is one of those training inputs xi, and then you have a hidden layer and then an output layer. So, let us look at what is the configuration of the hidden layer and what does the output layer actually try to do. So, it is a very special type of a feed forward neural network. What it does is it encodes its input xi to a hidden representation h, okay, and it uses an encoder function to do this. So, this is what the encoder function does. It first does a linear transformation. So, w is a matrix and xi is a vector, and you again have the bias b as a vector, right. So, let us look at these dimensions, right. So, let us try to fix some dimensions. So, suppose xi belongs to Rn, that is what we have been considering throughout the course so far, and let us say h belongs to Rd, okay. So, it is a d-dimensional representation. So, in that case what would w be? Yeah. So, w would be R n cross or other d cross n, right. So, it will multiply with a n cross 1 vector which is xi and give you a d cross 1 output, right. And similarly, b would also be d cross 1. And then on top of that you have this non-linearity g, which will be operating at element wise just as we had seen earlier. So, it could be any of the sigmoid functions, the logistic or tanh and so on. So, the end result is you have taken an input xi and encoded into a hidden representative h by using a linear transformation first and then a non-linear transformation, right. So, I refer to wx plus b as the linear transformation because it is a matrix multiplication. Now, once you have constructed this hidden representation, the job of the decoder or the latter half of the feed forward neural network, which is this half, is to take this encoded representation and then try to reconstruct x again from it, okay. So, again let us first look at the equation. So, this is the equation for the decoder, where again you first take the hidden representation, do a linear transformation, and then you again have some function or non-linearity on top of it, right. So, we will see what this function can be. So, we will refer to it as f for now, we will not say whether this is sigmoid or linear or what kind of a function it is, we will come back to it later on, okay. So, now let us again look at these dimensions. So, what is xi? Xi is again Rn and your h was Rd. So, you have to go from a d-dimensional input to an n-dimensional output. So, again your w star is going to be R n cross d. So, it will multiply with a d cross 1 vector and give you an n cross 1 output, right, and that will pass through some function and it will give you xi hat, which is a reconstruction of xi, okay. So, why are we trying to do this, right? We took an input xi, we computed its hidden representation by doing some non-linear and linear transformation, and then again we are trying to reconstruct xi hat. So, why are we trying to do this actually? So, the reason we are doing this is that we want to learn what are the most important aspects or most important characteristics of the input data xi, right. So, if you compute a hidden representation h, which is presumably smaller than your original input data, and from that hidden representation if you are able to reconstruct xi, right, then that would mean that this hidden representation captures everything that is required or everything that is required to reconstruct xi from the original input, right. So, the model will be trained to minimize the difference between xi and xi hat. So, you want to make sure that after passing through this bottleneck, which is the hidden representation, you are able to reconstruct xi and the reconstructed output is very close to the original input, right. So, can you see an analogy with PCA where you are trying to find this hidden representation or this most important elements of the original input xi. So, there we had used this linear transformation where we had taken the original input x and transformed it to a new basis and we had used that basis for representing the original input, right. So, something similar is happening here. We are using this hidden representation h to represent our original input. Now, let us consider a few cases. The first case is when the dimension of h is less than the dimension of xi. In this case, as I was trying to say earlier, if we are still able to reconstruct xi hat perfectly from h, then what does it say about h? It tells us that h is a loss-free encoding of xi. It captures all the important characteristics of xi, right? Just repeating what I had said on the previous slide. And now you can see an analogy with PCA, because h has all the important characteristics required from the original input data. So, it has probably got rid of all the noise or all the low variance dimensions or the correlated dimensions and so on. And this is just the compact representation, which is as good as the original representation, and from there you can reconstruct the original representation. And such an autoencoder where the dimension of the hidden representation is less than the dimension of your original input is known as an undercomplete autoencoder. Okay. Now, let us look at the other case where the dimension of the hidden representation is greater than the dimension of the original input. Okay. Such an autoencoder is, okay, I will tell you what it is called. So, we are looking at the case where the dimension of the hidden representation is greater than the dimension of the original input, right. So, now in such a case, the autoencoder could learn a very trivial encoding by simply copying xi into h and then copying h into xi, right. So, think of this from a compression point of view, right. So, now suppose you have 10 bits initially, right, and then you want to somehow compress it and store it only in 4 bits. And now this 4 bits should be such that it captures everything that was there in the original 10 bits, because you would want to reconstruct the original input again, right. So, this is what we do typically when we compress any of our files, right. We have a larger file, we compress it into smaller information while making sure that everything important is there, so that whenever I want to recover it, I can just recover it from there, right. So, this is definitely a hard task, but now what I am doing in this autoencoder is that I had 10 bits, I am actually giving it more bits now, because the dimension of h is greater than the dimension of the input, and then from these 16 bits I want to reconstruct the 10 bits. Now, this is a very trivial task, right, because all I could do is copy these 10 bits into the first 10 bits here, leave the remaining 6 blank, and then from those 10 bits just reconstruct the input. That is very, very trivial. If you give me more storage than what I originally needed, then definitely I can easily reconstruct it, right. So, this looks very trivial, and this is what it could do, right. Just copy the input to the first n bits. So, this was n and this was d, and we are looking at the case where d is greater than n. So, it could just copy the input to the first n bits and then just take it back to the output, just as I said in the case of you have 10 bits, 16 bits and then again 10 bits. It is very trivial to do this. So, such an identity encoding is useless, because you are just not running any important characteristics of the data. Your h is almost the same as xi, it also has all the useless information that xi had. In fact, it has slightly more, because it has these blank units also, but this is not really useful, right. Why would you want to actually learn such a hidden representation, right. So, it is not clear why would you want to do that. So, we will take a look at it, we will come back to why this is important. So, such an autoencoder is known as an overcomplete autoencoder, because it has the hidden representation has more number of neurons as compared to the original input. Now, let us look at a case where this would actually be important, right. So, this is a very rough intuition for why you would want an overcomplete autoencoder, right. So, let us consider the case where you have as input one of the features that you are looking as BMI. So, suppose you are trying to find out whether the person is likely to get a certain disease or not, right. So, whether he would have a heart attack or whether he would have diabetes and so on, and you are looking at various parameters or various medical parameters of that person, and one of them could be height, one of them could be weight, and one of them could be BMI. Now, for whatever reason you have not computed the height and weight and you have only looked at the BMI. So, now what has happened in your input, and all of you know that BMI is actually body mass index, which is a function of the height and the weight. So, now what has happened is that in your original input there was already this compact, your feature space was already compact, because you should have actually looked at both the features height and weight, but for some reason you have only computed BMI. And you could think of some other correlated features which are functions of many other features, but you don't look at all those features and just this final function of those features, right? So now in that case, if suppose your prediction is that this person has or has a high likelihood of having diabetes at some point in his life, then you would want to know whether it was the height or whether it was the weight which was responsible for this. So in your original input, your features are actually entangled and you would like to disentangle them, right? So you would want to go from this smaller feature space to a larger feature space where some of these entangled features get disentangled. So in those cases, you need such an overcomplete autoencoder. However, the problem still remains that there is no reason why the machine should actually learn to disentangle these features. It could still just simply copy the BMI here and then copy it back here, right? So that's why when you're dealing with overcomplete autoencoders, you'll have to do something special to prevent these kind of identity encodings, where you just take the input and copy it to the hidden layer and then copy it back to the output. So we'll look at what kind of special treatment you need to do to prevent these kind of identity representations. Okay. Here's the road ahead. So first we'll talk about the choice of fxi and gxi, right? So we did not say anything about what these functions f and g have to be. So we'll talk about those. And then we'll talk about the loss function. So I have just told you so far that we'll train this model in a way that xi is very close to xi hat, right? And I have argued that if we are able to actually achieve that xi hat is the same as xi, in which case presumably the loss would be 0. That means our hidden representation has captured all the important characteristics of the original data. Same as in the analogy of 10 bits to 4 bits to again 10 bits, right? If I am able to reconstruct this without any error, that means loss is 0, then these 4 bits or the hidden representation of my original x was actually able to capture everything that was important in x so that it can reconstruct x again as x hat without losing any information, right? So that's the loss function that we would want. Now what is the actual mathematical formulation for this loss function? That's what we'll see next, okay? So first let's start with the choice of f and g. So we'll consider two cases. One case when your inputs are binary, and the second case when your inputs are actually real numbers, right? So first we look at the binary case, okay? So now just some notation clarification. So remember our original data was this matrix X, which was m cross n. That means you had x1, x2 up to xm, and each of these was Rn, right? So now when I am referring to the entire row or entire data instance, I will use bold xi as I have circled here, and I want to refer to one of the elements of this guy, then I will use this notation xij, same as what I have written here. So what I am saying is that each of these xij's actually is a binary variable, okay? Now which of the following functions would be most appropriate for the decoder? So remember your input was binary, that means your output also has to be binary. You don't want to produce numbers arbitrarily large belonging to any, or you don't want to produce any real number, you want to produce numbers which lie between 0 to 1. So in such a case, what would be an appropriate loss function? What would be an appropriate function for the decoder? So remember I am asking you what would f be. So I am giving you 3 choices. It should be tanh or just a linear decoder or a logistic function. Which of these would be most appropriate? Logistic. Why would that be? Because it will make sure that your outputs are between 0 to 1. Tanh would give you outputs between -1 to 1, but you don't want that because your inputs were between 0 to 1. So when you are reconstructing, obviously you want outputs between 0 to 1. You don't want -1 to 1. And linear of course can give you any real number, which is not what you want, right? So if you produce any arbitrary real number like 100 and so on, your loss is going to be very high because your inputs were just 0 to 1 and you are producing these arbitrary real numbers which are very different from what your input was, okay? So in this case, the logistic function makes the most appropriate choice, and G is typically, that means the encoder function is typically again chosen as a sigmoid function. So it could either be the logistic function or the tanh function, right? So there is you could choose any of these as the encoder function, okay? Now let's consider the other case where your inputs are real valued. That means when you reconstruct something, you should again produce real values. That means your function f should take whatever is the input given to it and map it to some real numbers, right. So, that is what we want from this function f. Earlier in the binary case, we wanted it to map it to binary numbers, right. So, that is the difference that we have now. So, in this case, which of the following would be appropriate? The second one, right, because tanh does not make sense, because it will just produce -1 to 1, but you want to produce any possible real number, because some of these are actually higher than 1, greater than 1. Linear would be fine because it will produce any real number. Logistic is again not fine because it will produce numbers between 0 to 1. Okay. So, the logistic and tanh, as I said, would clamp the output to certain ranges, so that is not appropriate. Hence, you should choose the linear function. And again, in this case also, d is typically chosen as the sigmoid function. Right? Okay. So, the next thing that we look at is the choice of the loss function. Okay. And again, we will consider both the cases, where the case the first case is the inputs are real valued, and the second case is when the inputs are binary. Okay. So, let us look at the real case first. Now, here the objective of the autoencoder is to reconstruct xi hat to be as close to xi as possible. Now, we have actually seen this before. So, something similar before when we were talking about regression. So, now you want to produce real valued outputs and they should match your real valued inputs. So, what is an appropriate loss function that you can choose? The squared error loss function, right. So, what does this actually capture? It says that for all my input data x1 to xm, for each of these dimensions x12 up to x1n, right, I want to make sure that my original input, I will have a similar x hat reconstructed, where I will have x11 hat, x12 hat and x1n hat, right. So, I want to make sure that each of these pairs of variables are actually similar, and I can capture that by ensuring that the squared error loss between the ijth entry in my output is the same as this, or rather I could capture the squared error loss between the ijth entry in the output and the input. Okay, that is what this function is trying to capture. It's straightforward, similar things we have seen while we were doing regression, except that there we had y hat and y, but here we are just trying to reconstruct the input. So, there is no y here, we just have the x. Okay. And the parameters of the objective function are of course all the variables or all the parameters that we have in our network, which is w, w star, c and b. Okay. And the matrix or the vector way of writing this is the following. So, we have xi. So, what I am looking at here is I have gotten rid of this summation and I have just written it in vector form. So, let me just explain what this means. So, this is what xi would look like, right. So, this would be xi1, xi2 up to xin. Okay. This is the vector, and then you have the xi hat vector, which is going to be xi1 hat, xi2 hat up to xin hat, right. So, taking the difference between these two vectors, that is what this term is. So, what you will get is essentially xi1 hat minus xi1 up to xin hat minus xin, right. And then you are taking the dot product of this vector with itself, which will essentially give you this summation, right. So, the dot product of this vector with itself is actually going to be this summation. It is going to be the sum of the squares of the elements of this vector, and that is exactly what we wanted. So, this is a more compact vectorial way of writing the same thing. Okay. And now we can just train the autoencoder by treating it as a regular feed forward neural network. This is just like any other feed forward neural network. You have defined the loss function and you can just use backpropagation to train it, right. But, and in this case all we will need is a formula for the gradient of the loss function with respect to your parameters, which are w and w star. I have again ignored the biases and the biases here b and c. So, we will also need dou L theta by dou b and dou L theta by dou c, right. So, these two gradients also you will need, but these are generally the easier ones to handle. If you know how to compute this, the b and c are very easy. Okay. So, let us look at this. Now, what do we need for backpropagation? As I said, we will need this gradient, right, all these 4 gradients, but let us focus on one of these. Now, we have already done backpropagation and we have looked at arbitrary neural feed forward neural networks there, right. We did not have we just said that there are L hidden layers, and in this case L is equal to 1, right? Or rather we had said there was L minus 1 hidden layers and the Lth layer was the output, right? So in this case L minus 1 is equal to 1, that means there is just one hidden layer. So it doesn't matter, we had actually derived it for the general case when L is equal, when the number of hidden layers is L minus 1, and here we just have one hidden layer. So it's much more simpler than what we had learned. And even for the number of neurons in each of these layers, we just assume general that it could be Rn, and in this case we would have some Rd which is less than n, or it could even be greater than n, right? So but it doesn't matter, because whatever algorithm we had or whatever equations we had derived for backpropagation, they did not care about what this n or d was, we just derived it in generic terms, right? And the same for the output layer, right? We did not assume any number of inputs, any number of neurons in the output layer. We again said that it has some k neurons, but there the catch is, in the earlier case when we had derived backpropagation, we were dealing with classification, and we had these k classes that we want to predict at the output, and in which case our loss function was actually the cross entropy or the negative log likelihood function, right, where we were trying to maximize the probability of the correct class out of the k given classes. But here our loss function is slightly different. It's actually the squared error loss between the input and the output. So now, given this difference in the loss function, does it mean that everything that we learned in the previous lecture on backpropagation, we just have to throw it all away? Because now there's a new loss function. That means my gradients are going to be very different from what I had derived for the backpropagation loss, where I was looking at the cross entropy loss as compared to the squared error loss. So does it mean that I'll have to throw away all the hard work that we had done in that course, in that lecture, or can we reuse something from them? We can reuse, right? So let's look at what we can reuse, and I'll just give you an intuitive explanation for that. So you can think of this as a composite function, right? You're taking your input, passing it through a lot of functions, and then arriving at the output, and then your loss function is actually a function of the output itself. So what we have is something like this, right? We have a situation like this, that you had an input x, you computed some function of it, say x square, right? So I'll call this as y1. Then you computed some other function of it, say y1, say log of y1, right? So this was log of y1. So in effect it is actually log of x square, because y1 is equal to x square, and then some other function, and then finally you had the output. Say you had this other function which was sine of, if I'm calling this y2, so say this was sine of y2, and finally you had this function which was e raised to y3. So you have a very complex composite function of your original input, right? And this is your final output function that you are considering, which is e raised to y3. Now the way you would do this is, if you want to take the gradient of dl with respect to your input dx, right? In that case what you would do is you just apply the chain rule. You will write it as dou L by dou y3, dou y3 by dou y2, dou y2 by dou y1, and then dou y1 by dou x, right? And this is something very similar that we had done in the backpropagation lecture. We had constructed this chain, and then we had attacked every element of this chain and derived how to deal with that, right? Derived a neat expression for that. Now the question which I am asking you is that in that lecture we had assumed a certain L, and that L was actually cross entropy. But in this lecture I have actually changed the L. What I am saying is the L is actually equal to the squared error loss. Now does that mean that I have to throw away all this work that I had done? No, right? So even in this example, if you look at it, suppose I change this function from e raised to y3 to say square root of y3, right? So I've just changed my L. But notice that all of these other guys are going to remain the same, because y3 is still sine of y2. So that the derivative of y3 with respect to y2 is not going to change. Even though I've changed the output function, the loss function, everything else is going to be remaining the same, right? So that means all these portions I could just reuse from the time when I had computed for this chain. I just need to rework on this final expression and plug it in, right? So that's why all the work that we had done in the case of backpropagation will not go to waste. In particular, everything that we had done, so let me just go to the next slide. So in particular, everything that we had done for this portion of the network, right, which is actually dou A2 all the way up to dou W, right? So okay, so let me write it as this. I want dou L by dou W So I can write it compactly as dou L by dou A2 and then dou A2 by dou W, right. So this portion is not going to change because I have not changed any of the functions here. I have just assumed sigmoid or logistic or the same kind of network. The only thing I have changed is something at the output layer. So I just need to recompute this and the rest of it can be reused, right. So that's the intuition which I wanted to give you, and that's exactly what's written on this slide. So I have written it as dou L theta by dou W star. That's the first gradient I have interested in, and I could write it as dou L theta by dou H2 by A2 and dou A2 by W star, right. Now this portion, as I was trying to say, is something that we have already seen in the backpropagation lecture and nothing has changed in the network in that part. So you can just reuse it as it is, and this portion is something that we need to recompute, right. That's the only thing that we need to recompute and plug it into our backpropagation code or the algorithm which we had in the previous lecture. And similarly, if you want to do dou L theta by dou W, it's the same idea here, that you could write it as the following chain, and this part of the chain you already know how to compute from the backpropagation lecture. All you need to do is change the loss function and just try to find the derivative of the loss function with respect to your output layer, which is H2. That's the final thing that you have changed. Just as in my toy example, I had changed e raised to y3 to square root of y3, right. That's the similar change that I am trying to do here, okay. Fine. So all we need to do is dou L theta by dou H2, but dou H2 is the same as xi hat, right, because that's my output and my output I am calling it as xi hat. So I need to take actually the derivative of this. So I am just using the vector form here. I could have also written it as this summation over I equal to 1 to n xij minus x hat ij the whole square, right. I could have also written it as, I am just writing it as a vector here in the vector form here, right. But this quantity ultimately is going to be a scalar because it's a dot product between two vectors, which is a scalar. So what I'm doing here is taking the derivative of a scalar with respect to this vector. So what is that derivative going to be? It's going to be a vector, okay. And I'm just so we have done similar stuff in the past, so you can actually easily work this out. So this will actually turn out to be the following vector, which is 2 times xi hat minus xi, right. So this is very simple. I have just computed this, and all I need to do is go back and change my backpropagation code and change this derivative of the loss function with respect to the output layer, and the rest of the code I can just reuse it as it is, okay. So now similarly, so we have both of these ready, okay. Now let's look at the other case when we have binary inputs, okay. This is the this is something different that we'll have to do here. So we'll now look at the second case where the inputs are binary, okay. So first we look at the case when the inputs were real numbers and hence your outputs also needed to be real numbers. Now we look at the case where the inputs are binary and hence your outputs also need to be binary, okay. Now here, so each of these guys is actually a sigmoid function. So it's an or rather, if you look at the output, you could divide it into two parts. So this is the pre-activation and this is the activation, right. So this is actually the pre-activation and this is the activation, right. So this activation is actually chosen as a sigmoid function, or the logistic function, not the sigmoid function. Of course, logistic is a sigmoid function, but the logistic function, which was 1 over 1 plus e raised to minus z, right. So logistic of z is equal to 1 over 1 plus e raised to minus z, okay. And remember that this sigmoid function was element wise. That means this A is a vector. It has elements a1, a2 up to an, and then when you apply the sigmoid to it, you get h, which is going to be sigmoid of a1, sigmoid of a2 and sigmoid of an, right. So it's just the sigmoid applied to every element of the activation layer. That means every element of this vector which I have circled, okay. So now in this case, your outputs are going to be between 0 to 1, right, because your inputs were also between 0 to 1 and your sigmoid or the logistic function is going to give you clamped outputs between 0 to 1. So since this is between 0 to 1, we could actually interpret it as probabilities, right. So we could say that whatever you are reconstructing is actually telling you that with 0.8, suppose the reconstruction value is 0.8, then you could think of it that with probability 0.8, it's telling you that the output should have been 1, right. And if it tells you that the output is 0.2, if the sigmoid gives an output as 0.2, then you could think of it that with probability 0.2 the output was actually 0, or rather the input was 0, because your input is the same as the output, right. So that's one way of interpreting it, and this way of interpreting it, why does it make sense? So we'll just look at that, right. So before that, if I don't give you this interpretation, and remember that the sigmoid is going to produce values between 0 to 1, but not necessarily 0 and 1, right. It will try to be as close to 0 when the input is 0, but it could also produce 0.05 and so on, and when the input is 0.9, it could also produce something like 0.95. So at the output also you are going to get these vectors which are which would look something like this, right. And suppose your input was 0, 1, 0, 1. Now can you think of a suitable loss function for this? Yeah, so again these are two vectors, these are x hat and x. So once again you could have just gone with a squared error loss, right. You could have taken the squared error difference between these two and you could have been fine, right. So that's definitely one way of going about it. But whenever we are looking at these binary inputs and whenever this probabilistic interpretation is possible, we tend to do something better, which is look at the cross entropy loss instead of looking at the squared error loss. So I'm not saying that the squared error loss is wrong in this case, but you could also use this cross entropy loss, and in practice for our binary inputs the cross entropy loss often works much better than the squared error loss, right. So let's see what I mean by the cross entropy loss. So remember that you have n outputs, right. That's why this summation. Let's not worry too much about what's written inside for the time being, I'll explain that, but I just want to explain the summation first. So what you're saying is that for each of these green guys at the output, you're going to make some loss and you just want to sum over that loss. That's what we are trying to see. Now ideally you could have just written it as, just done what you had done before and written this entire, replace this entire box by this squared error loss, and that would have been just fine, right. Of course there should have also have been this summation I equal to 1 to m here, because you are going over all the m training instances, and for each of the m training instances you are trying to minimize this loss. So this two summations followed by the squared error loss would just have been fine, but instead of that I have this something special here. Okay, so let's look at what this special quantity is. Okay, and now for that, remember that I am trying to interpret each of these inputs as a binary random variable. I am saying that they can take values 0 or 1. So I can think of it that when I am given that this value is 0, I can write it as this deterministic probability distribution where I have P and the probability mass is entirely concentrated on the 0 value, and the probability mass on the value 1 is 0. This is something similar to what we had done earlier when we were given these labels. Suppose it was apple, orange, mango and banana, and the class label was given to us that this is an apple, then we could still write it as a probability distribution where all the mass was concentrated on apple and everything else was 0. So I'm saying something similar here, right. So you could think of it that two possible values can occur here, 1 and 0, and if I tell you this is 0, right, then I'm telling you that with probability 1 it is 0 and with probability 0 it is 0. So I can still write it as a probability distribution. Now the same thing I can have at the output. So for this unit, when I'm trying to reconstruct it, and if I produce the output as 0.2, then I can, or rather let's say 0.8, then I can say that with 0.8 probability I am predicting a 0, and with 0.2 I am predicting a 1. Right? So now I can think of this again as two probability distributions, and once I have two probability distributions, I know that cross entropy is the right or a better loss function to look at, right. And what's cross entropy actually? In this case it would be given by summation I equal to 1 to 2, right, or rather I equal to 0 to 1, because those are the two values it can take, P of I, right, into log of Qi plus so P of I into log of Qi. That's how I can write it. Okay, so let me just, since there are only two terms, I can just expand this summation, right. So I can write it as Pi, or rather P0 log of Q0 plus, of course there is a minus sign here, there is a minus sign at the out, P1 log of Q1. I can just open up because there are only two terms, so I can write it as this. Is that fine? Okay. Now also I know that there is this relation between P0 and P1, that P0 is actually 1 minus P1. Similarly, you have this relation between Q0 and Q1, that Q1 is equal to 1 minus Q0 because the sum is going to be 1. Okay. Now, let us look at this sum, right. So, in the binary case this sum becomes interesting, because now suppose your input xij, right, which is the entry that I am looking at, suppose that was equal to 0, in which case all the probability mass would be concentrated on P0 and P1 would actually be equal to 0, which means the second term would disappear. Okay. On the other hand, if xij is equal to 1, then the reverse situation would happen, that everything would be concentrated on P1, that means P1 is equal to 1, and this chi would become 0 because P0 is going to be 0, right. Okay. So, there is this another way of writing it, that you could say that instead of writing P0 and P1, you could just write it as xij, right, into log Q0 plus 1 minus xij into log of Q1. So, now let us look at it again. So, when xij is 0, first, which is the same which happened here, just an equivalent, the same thing, right, because whenever xij is 0, P0 is equal to, sorry, it should have been Q1 and log Q0. Sorry, I made a mistake here. So, it should have been xij into log Q1. So, or rather let me just rewrite it. So, this is going to be, actually I can write it as I look at this term first. So, I can write it as xij into log Q1, and then the second term I am going to write it as 1 minus xij into log of Q0, right. And then I am going to simplify this further, but let us see what is the consequence of this. So, now whenever xij is equal to 1, this term will remain and the second term will disappear, and that is exactly what was happening in our original formula, right. So, this is just an equivalent way of writing. Whenever xij is equal to 0, this term will disappear, but this term will remain. That means log Q0 will remain. This is exactly what was happening in our original formula, right. So, now I have given you why I can replace P0 and P1, or rather P1 and P0 by xij and 1 minus xij. And now I can make a similar argument for x hat ij also. So, I can think of Q0 as whatever is predicted at the output, right. So, I can treat Q1 as whatever is predicted output. So, whatever my sigmoid function predicts, I can think of it as it is predicting the probability of getting a 1, right. So, it is just predicting the heads probability or the probability of getting 1. So, I can, instead of Q1 I can write it as xij hat, and similarly instead of Q0 I can write it as 1 minus xi hat ij, right. So, do you get that? So, this has become very messy. So, let me just clean this up and I will just go over this again, right. So, what I was trying to tell you is that in the ideal case you could have just replaced this by the squared error loss. But since you are dealing with binary inputs, you can do something better, because you can interpret the outputs as probabilities. So, when you get a 0.2 here, you can interpret it as it is telling you that the probability of this unit being 1 is 0.2, it is very less, and that is the same as saying that the probability of this unit being 0 is 1, right. So, you can interpret this as a probability. Now, if you think of it that way, then you can say that at the input you are actually given a probability distribution. So, which tells you that in the first case your probability distribution looks like 1 0, right, because all the mass is focused on the value 0, because your input is 0 at that case. And now suppose your output was 0.2, right, and 0.2 is what you are treating as a probability of, so this is the probability of 1, this is the probability of, this is the probability of 0, oops, and this is the probability of 1, okay. So, if your output is predicting 0.2, that means it is predicting 0.8 for 0 and 0.2 for 1, okay. Now, if you think of it this way, then you can capture the loss function between these two guys using the cross entropy formula, which is going to be summation I equal to 0 to 1 pi log Qi. Is that fine? Okay. And now I just said that since there are only two terms, I can just write it as P0 log Q0 plus P1 log Q1. Then I focused on this relation between P0, P1 and your input. So whenever your input is 0, okay, your P0 is going to be 1. So then I can just replace P0 by 1 minus my input. Right? So if the input is 0, then this guy is going to be 1, and that's exactly what this expression is also going to be. So I can write it as 1 minus xj log Q0, and similarly for the second guy, whenever my input is 1, this guy is going to be 1. Whenever my input is 1, this P1 is going to be 1. Whenever my input is 0, this P1 is going to be 0. So I can just replace P1 by log by xij, and now you can see that this expression evaluates to the same as this expression, right? You can substitute the value of xij 0 or 1, you will get the corresponding P0, P1, which would be 1 or 0 depending on what your input was, and these two expressions will evaluate to the same thing. So just as I replace the P's by xij's, I can similarly replace by the Q's by xij hats, right? Because once again Q0 is nothing but 1 minus whatever my output was predicted, because whatever is predicted I am treating it as the probability of getting a 1. So 1 minus that is going to be the probability of getting a 0, so that is what Q0 is. And similarly Q1 I can replace by x hat ij, and so that is exactly what I have done in this expression here. So now this expression, every term in these n terms captures the cross entropy for that particular random variable, right. So this is the original distribution P for this random variable, this is the predicted distribution Q for this random variable, and I have just told you that the cross entropy between these two distributions can be written in this simple form as a function of xij and x hat ij. So this is a standard thing to do when you are dealing with Bernoulli random variables, so you can go back and read up a bit about it. But for now, I guess with this explanation it should suffice to know why this expression is used. And remember that I am not telling you that the squared error function was bad, I am just telling you that instead of the squared error function, cross entropy loss function works better when you are dealing with binary inputs. Okay, fine. So with that, let us proceed. And the other way of looking at it is the following. You can now look at this expression and tell me when is this expression going to be minimized. Okay, so we have xij and x hat ij. You can see that this expression will be minimized only when xij, or rather x hat ij is equal to xij, right. So now xij could take value 0 or 1, okay, and now x hat ij could take 0, 1 or 0, 1. So you can see that for these two combinations, the value is going to be minimized only when x hat ij is actually equal to xij. That means if xij was 0, then x hat ij should also be 0, and similarly in this case also, if xij was 1, then the expression will be minimized only when x hat ij is equal to 1. So let us see this, right. So suppose xij was 0, that means this term is going to go to 0, but this term is going to remain. And now if your x hat ij was not equal to 0, then you will get some log of 1 minus x hat ij as the loss, right. But if x hat ij was also 0, then you would get log of 1, which is 0. So this whole expression would then evaluate to 0, which is the minimum possible value for this expression, right. So that means if xij is 0, then this expression will be minimized only when x hat ij is also equal to 0. Similarly, if if xij is 1, okay, then this 1 minus 1 will give you 0, so this term is going to disappear, but this term will remain. So this will just be log of x hat ij, because xij is equal to 1. Now if x hat ij is also equal to 1, then this will become log of 1, which is 0. That means again this expression will attain its minimum value when x hat ij is equal to xij is equal to 1, right. So this expression will attain its minimum value in two cases, when xij is equal to x hat ij is equal to 0, or when xij is equal to x hat ij is equal to 1. So compactly I can say that this expression will attain its minimum when xij is equal to x hat ij. That is why this loss function makes sense. Okay. Now again we have this problem that we want to use backpropagation to train this network, And once again, for backpropagation, we will need the following gradients, the gradients of the loss function with respect to W and W star. Okay, this is what we are going to need. And I'm going to make the same argument again, that whatever hard work you had done in the backpropagation lecture, you can just reuse all of it, because the only thing you're changing is this final loss function. So you just need to compute the gradients with respect to this loss function, and everything else is going to remain the same, right? So that's exactly what I'm going to do on this slide. So whatever is in the boxes here, these two boxes, that is something that you have already computed. And now what I'm going to compute is the stuff which is outside the boxes. So let's look at that. So I'm interested in computing this dou L theta by dou H2. This is the derivative of a scalar quantity with respect to a vector. So it's going to be a vector. And I'm going to follow our usual recipe, which is H2 is actually equal to H21, H22 up to H2n. So I'm going to consider any one of these guys, which is H2j. I'm going to compute the derivative of the loss function with respect to this one entry. And once I have that, I'm going to construct the entire gradient, right? So now I'll have this dou L theta by dou H2j. Right? And once I have that expression, I'm just going to generalize it to all the other entries in this vector. So let's look at that expression first. Okay. So now if you look at this, actually it does not have an H2j, right? But we know that H2j is the same as x hat j, or rather x hat ij, right? For the ith input, it's going to be x hat ij, because H2 is equal to x hat I. Okay, you can just see it at the top left corner of the slides. So H2 is equal to x hat I. So this is nothing but dou L theta by dou x hat ij. So now I want to take the derivative of this quantity with respect to one particular xij. And remember that this quantity has a sum which is indexed over j. So j goes from 1 to n, and I am looking at one particular j. So that means if I expand this sum of all the j's possible, the derivative with respect to all but one is going to be 0, because they don't depend on this particular j. So if I am looking at j equal to 3, then the term which has x hat I1 is going to, the derivative of that term is going to be 0. So of all these terms in the expression, only that term where j is equal to the j which I am considering is going to remain. Okay. So that means only one term in the summation would remain, and for that one term, so let me just get rid of the summation, right. So that means only one term in the summation would remain. I am trying to find the derivative of this quantity x which has a lot of xij's with respect to xij. So now this is of the form a log x. So the derivative would be a over x, right. So that's exactly what I have written here. And similarly for the second guy, this is 1 minus a into log of 1 minus x. So the derivative is going to be 1 minus a over 1 minus x. And of course there is this minus sign here which will then get adjusted appropriately, right. So that's how this expression has been computed. That's very straightforward. And now I also need the derivative of h2j with respect to a2j. So remember that h2 is equal to sigmoid of a2, which means it's just an element wise sigmoid, right. So I just need to compute the derivative of the jth entry of h2 with respect to the jth entry of a2. All the other derivatives are going to be 0 because they don't depend on that particular entry of a2. So now that is just going to be sigmoid of a2 into 1 minus sigmoid of a2, right. So I have computed these two quantities. I can just plug them back into our backpropagation code. The rest of the code is going to remain the same, and I have the gradients ready with me. Okay. Right. And as I said, once I have this one guy, I can just extend it. I can just generalize it. So I just had these j's here, right, for h2j. So I can just replace the j by 1, 2 up to n, and I'll get the same expression. Okay. So that's the end of module 1, where we introduced autoencoders. What we showed is that they are actually just like any other feed-forward neural network, except that they have this special objective that they want to reconstruct the input. And the reason they want to reconstruct the input is they want to first create a bottleneck, which is this h hidden representation, and then try to reconstruct from there. And just as I gave you that compression analogy, that you have this 10 bits, you want to compress it to 4 bits, and then reconstruct the entire input again. So this will happen only if these 4 bits capture everything that is required or the most important characteristics of your original input, right. And then we could have a loss function which tries to capture the difference between my original input and my reconstructed input. Now we argued that this loss function will be dependent on the nature of your input. So for the real inputs it was straightforward, we just said that we can use the squared error loss function. For the binary inputs we actually did something special. We said that we can actually use the cross entropy, and then we had this funny way of writing the cross entropy which was this xi into log of x hat and 1 minus xi into log of 1 minus x hat, and just gave you some intuition that that's the same as writing p log pi log or rather p0 log q0 plus p1 log q1, right. And I just gave you some explanation for doing that. You can go back and check on how do you write the cross entropy for Bernoulli random variables, and you will see that this expression makes sense. And once we had this expression, computing the gradients was easy. So the other thing that we relied on is that in the backpropagation lecture we had taken care of everything up to this point, and in this lecture we have actually changed the loss function. So one loss function was the sum of squared loss errors, and the other loss function was the sum of cross entropies, whereas in the backpropagation lecture we had only dealt with cross entropy. But the case that we made is that since you have this chain and all you have done is change the last function in the chain, right. You have changed this L function, all the other functions you have not changed. You can just reuse the computations from these, or you can just reuse the code that you had written for these in the backpropagation assignment, and you just need to change this last guy to adjust for the change in the output layer or the change in the loss layer. Okay. So with that we'll end the introduction to autoencoders, where we have we have actually covered how to train an autoencoder using backpropagation. Okay. So that's where we'll end.